Hi guys, this is Becky, and in this video we're going to look at the different types of bonding models that we can use to explain properties in compounds. So the goal of this video is to be able to describe how different units are arranged in different types of compounds depending on bonding type, and then to be able to relate the type of bonding that is present to macroscopic properties. So the properties that we can see, how does that relate to the arrangement of molecules on an atomic or molecular level? So in our last class, when we met, we looked at different properties of several compounds. So we had 8 substances, and we tested a couple properties. We tested, do they conduct as solids? Did they dissolve in water? And then did they conduct when they dissolved in water? And when we looked at that, the data that we gathered from these tests, we found that we could separate them essentially into 3 categories, where we had some that conducted as solids, and those that conducted as solids didn't dissolve in water. We had some that did not conduct as solids, but dissolved in water and then conducted when they were dissolved. And then we had some others that didn't dissolve, that did not conduct as solids, did dissolve, and some didn't, but they did not conduct when they were dissolved in water. And so if we look at these three substances that we have, right, the differences between these, and we look at what they were made of, these things that conducted as solids and didn't dissolve in water, this was copper and aluminum. This was sodium chloride, sodium acetate, and this was something like sugar, citric acid, etc., paraffin. So if we look at these, we can think about how these related to each other, right? So if we look at the things that conduct as solids, these tend to be made entirely of metal ions or metal atoms, metals only. These guys here were metals and nonmetals. And these guys here were nonmetals only. So if we look at this, the composition definitely indicates that they are different types of stuff, right? They have very different properties, and they're made of different things. So how does what they're made of relate to these macroscopic properties, to dissolving, to conducting, and to thinking about how those things behave? So the macroscopic properties that we're observing absolutely 100% depend on what the substance is made of, because what the substance is made of will determine the type of bonding that is present, and the type of bonding that is present will determine the properties of that substance. Okay. So when we break it out by composition, and we look at things that are composed of different materials, like when we look at things that are composed of only metals, and we look at things that are composed of metals and nonmetals, and we look at things that are composed only of nonmetals, right? Something has to be different about how these things are arranged to account for the differences in properties that we see, right? We know things about metals. Metals tend to be shiny, right? They're malleable. They're bendy, right? They tend to have, they conduct as solids. And they tend to be solids at room temperature, with exception of mercury, which is a liquid, but they tend to be solids at room temperature. If we look at the things that are made of metals and nonmetals, based on the lab activity that we did, these things are solids at room temperature, right? They are crystalline. They look like they were made of little crystals. They do not conduct as solids, but conduct when dissolved. And then nonmetals, things that were made of only nonmetals, tended to be, these were solids or liquids. They don't conduct. Some dissolve, some don't. And some conducted and some didn't. One weakly conducted, but mostly they don't conduct in solution. So something has to be different about how these atoms are arranged. And so when we look at this, we're going to look at the types of bonding that's present in things that are contained in nonmetals. We're looking at covalent bonding. In things that are contained of metals and nonmetals, we're looking at ionic bonding. And in things that are just metals, we're looking at metallic bonding. So let's look at each one of these in a little bit more detail. So when we look at ionic bonding, remember we've talked about this before where we have ionic compounds as being made of a metal ion and a nonmetal ion. Because we talked about this, the difference in electronegativity is so great that those electrons are transferred from the metal ion to the nonmetal ion. So what I end up with are these ions, and that these ions are held together by only the electrostatic charge interaction. The fact that positive charges are attracted to negative charges. So if we look at this, what happens is that I end up with this crystalline pattern here where I have these valence electrons only on the nonmetal atoms. So I have positive, negative, positive, negative, positive, negative in this kind of three-dimensional crystal array. So this three-dimensional where we have positive charges as far apart as possible from other positive charges and negative charges as far apart as possible as from other negative charges. Okay. Key thing here, and what makes this thing so cool, is that the interaction between this ion and this ion is an ionic bond. There's no difference in strength between this interaction and this interaction, or this interaction, or this interaction. So essentially what you have is this kind of three-dimensional network, or this three-dimensional charge interaction between these ions. These ions don't overlap, right? But because of this electrostatic charge attraction, which is strong, right, these compounds tend to have very high melting points and boiling points. Every single one of them is a solid at room temperature, right? Because in order to melt it, I have to break this electrostatic charge interaction here, which is not going to be easy to do. So they tend to have very high melting points and boiling points. They tend to be water soluble. There's exceptions, of course, but they tend to be water soluble. And then when they do dissolve in water, they conduct electricity. Because what happens when they dissolve is they do something called dissociate. And so what we end up with is we end up with positive ions that are surrounded by water and negative ions that are surrounded by water. And so when you separate those ions away from each other, those ions are free to move around, which means that they can conduct electricity. Remember, the only thing that is required for electricity to be conducted is having charges that can move around. When ionic compounds are dissolved in water, you have charges that can move around. Okay, they're brittle. They break easy because if you think about it, if I try to slide this guy here past this guy, I'm going to end up with negative charges next to each other, and then it's going to break rather than bend, right? So very strong directional bonding results in this idea that you have this compound, very high melting point and boiling point. They tend to be water soluble, and then they conduct electricity when they're dissolved or when they're melted. So if I were to melt salt, melted salt would be a very good conductor of electricity. Okay, in contrast, covalent bonding, when we talked about this, we said that this was between two things that have very similar electronegativities. So if we're looking at the distribution of electrons, those electrons are right here. They're right in between those non-metal ions, and they're held and they're shared equally. So what we end up with is these small units here, where the strength within the unit, the force that holds this atom to this atom, is much, 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 much stronger than the force that holds this unit to this unit. Okay, so the forces within are much, much stronger than the forces between, which leads to the formation of these things called molecules. Covalent compounds exist as molecules, which are these small distinct units. Ionic compounds do not, because of the nature of ionic bonding and that idea where there was no difference between the interactions between any of the cations and any of the anions. So these form these small stable units that are called molecules. And small stable units within the substance are called molecules. Right? Because of the presence of these molecules, these tend to have, they can be solids, liquids, or gases at room temperature. They tend to have very low melting points and boiling points. Because the force that holds the molecules to other molecules tends to be relatively weak. Okay, they do not conduct electricity because there's nothing here that can dissociate, or there's nothing here that can carry a charge. These electrons are locked in place, and because those electrons are locked in place, they cannot move. They cannot conduct electricity. Some of these dissolve and some of them do not, just down to the nature of the structure of each of these individual units. There's a lot of variation in properties here. In particular, you'll notice the one that we did in class where we looked at citric acid and acids in general tend to behave a little bit weirdly. They're molecular compounds, but they tend to behave a little bit oddly in terms of the general properties of molecular compounds. So molecular compounds or covalent bonding form these things called molecules. They can be solids, liquids, or gases at room temperature. They don't conduct. Some of them dissolve, some of them do not. Lots of variation in properties here based on the structure of the molecule. So when we look at metallic bonding is a little bit weird because metallic bonding, we were thinking about ionic and covalent, we're looking at differences in electronegativity. When metallic bonding, what you have is an interaction between these two metal atoms, neither one of which has a particularly high affinity for the valence electrons that each one has. So instead, what happens is that these valence electrons that are attached to the metal, when they are interacting, are no longer attached to the metal. So what forms is we call it the C of delocalized valence electrons. So delocalized means that they're not associated with a particular atom. Which means that they are free to move throughout the structure. Because of these delocalized valence electrons, and because they're free to move throughout the structure, metals conduct electricity when they are in solid form. Because these electrons, like this where we're shading area, are free to move, and so they can carry an electric current. They're bendable because this interaction is strong, but it's non-directional. It doesn't matter what metal ion is next to what. If I rearrange the structure and I put this ion next, or this metal next to this ion, nothing matter. It doesn't matter. The force of the metallic bond doesn't change because of the nature of these delocalized valence electrons. So it's a strong but non-directional bond, which means that they're going to be bendy. So they're malleable. They don't dissolve in water because there's nothing for the water to interact with. And they conduct electricity as solids because those valence electrons are free to move throughout the substance. Without that, they will not conduct electricity as solids. So when we look at this, and I know that we went through this pretty quickly, but the type of bonding that is present determines the macroscopic properties. The properties that we can see are determined by the type and the nature of the bonding that is present on an atomic level, on a molecular level. So we can use the macroscopic properties to predict something about the bonding, and the bonding to predict something about the macroscopic properties. So I have an unknown substance. It's a white crystalline solid at room temperature, has a melting point of approximately 210 degrees Celsius. It's water soluble and does not conduct as a solid or in an aqueous solution. What type of bonding is likely present in the unknown substance? Okay, think about that. Make some notes, take a guess, or think what evidence do you have to support the claim that you're making, and bring that with you to class next time.